Yeah, I think everything works now. So I am Prathamesh, and a final year undergrad student from India, and I'm going to talk about an image processing dialect and MLIR. So let's just start with having a look at the challenge. So the challenge is to make image processing faster, to make our life easier. Don't you agree? So let's have a look at one of the potential solutions to it. So a potential solution involves using vectorization. So there are other solutions like tiling and stuff, but I won't be emphasizing on them, at least for this talk. So let's dig in then. So let's have a look at how vectorization is usually done on a CPU. So the usual method to do vectorization on a CPU is to use these single instruction multiple data SIMD intrinsics in C++. So people can just write their code in C++, which is then directly converted to the vectorized low-level code. An important detail to note about this is that all of this is usually hardware specific. So you'll have to use different intrinsics for AVX2, 5 and 2, or whatever hardware you actually want to use. So please recall that the intrinsics code looks something like this. So this is actually an example of an AVX2 machine. So when dealing with these SIMD intrinsics at such a higher level, we are usually presented with two options. So the first option is to have the manual handwritten re-implementation of each and every algorithm which you want to implement. So as you can already guess that this will lead to a lot of code duplication, which will translate to more code, which eventually leads to more code maintenance. So nobody wants that, right? So the second method involves using a custom wrapper. So many of these SOTA techniques use a custom wrapper which tries to target all of the different intrinsics in C++ via a generic API. So let's have a look at such an example. So an example for this is this universal intrinsics wrapper. So it is used by OpenCV. So you can see that universal intrinsics targets all different kinds of hardware with just one single API. But this actually has some drawbacks as well. So you can see that we are trying to wrap around the intrinsics exposed in C++, which are themselves a wrapper for vector registers. So we are inevitably adding more code, which will translate to more code maintenance. The second thing is that whenever a new hardware technology comes along, we might actually have to add the support for it starting from scratch. So this is not always desirable. And in the process of adding support for a new technology, you might actually have to make some non-trivial design decisions. So let's take the example of scalable vectors. So scalable vectors was not a very known thing a decade back. So if someone would have written a wrapper then they might have to make some non-trivial decisions in the API itself to incorporate these new scalable vectors. So all of these problems can effectively be solved by a potential solution. So a potential solution which I present in this talk is to use compiler lowering passes for vectorization in image processing. So this basically leads me to three major things. So the first thing is that I can generate a vectorizable lower level IR. So I can generate LLVM IR and let LLVM do the heavy lifting of generating target specific code. The second thing is that the only place where I need to add support for a new hardware is the compiler stack itself. So we won't be dealing with anything on a higher level. We will just be dealing with the compiler, and the compiler will supposedly have the support for the hardware which we want to target. And the third thing is that all of the algorithm specific or the image processing specific stuff in this case will be confined to a single lowering pass or a single dialect. So any person who actually wants to have a look at the algorithmic implementation will only have to get their hands dirty with a certain dialect at a higher level and won't actually have to worry too much about the lower level details. So after having a look at the problem and a potential solution, let me present you our approach to it. So we chose MLIR to implement these lowering passes. So the three main selling points for us in the MLIR ecosystem is the concept of this modular and reusable dialects. So this actually provides a lot of interoperability between different levels of abstractions. The second point is that there already exists some simple infrastructure for rewriting, so we won't have to do too much of all that compiler work by ourselves. And the third thing is that low-level code generation from the LLVM IR level is a well-tested thing. So there are less chances of bugs creeping in because of mistakes which were not made by us. So due to these reasons, we made the decision of creating a MLIR dialect for image processing. So let's have the look at the dialect itself. So we call it DIP, or digital image processing. So as you can see, the DIP dialect lowers down to the LLVM IR level via MLIR's lower level dialects like memref, vector, affine, SCF, and all of those things. Additionally, having a dialect at this abstraction level allows us to do image pre-processing stuff at the MLIR level itself. So as we know that many models can be translated to MLIR, which might require an additional image pre-processing step before passing the input to the inference function. So this can be effectively done with this dialect. So a model can be lowered to an MLIR function, which can then be passed the input, which we get after doing the image pre-processing at this step. The third thing which we provide here is we also raise this dialect in the form of a C++ library. So we provide a C++ library which can use all of the operations present inside this dialect. So all of the operations which we provide are wrapped around functions and are put inside a file, let's say dip.mlr, which is then lowered to dip.o using the lowering passes we have created. This object file can then be linked at compile time with the example the user wants, and the user gets all the power of image processing with MLIR by just calling a C++ function without actually having to get their hands dirty with MLR and other compiler details. So this complete flow is a part of the Buddy compiler project, and I've also attached a reference to it. So let's just have a look at a brief example for the DL inference workflow. So you can see that we can read an image using the OpenCV's API into a CVMAT container. Now, this container is a popular container for storing images, and a lot of open source projects actually use this. So the container which we have created for our dialect is compatible with this, and we can actually get the image in the form of a memref, which will then be required to pass as an input for our function. So you can see that after getting the input in the required format, all we need to do is just call the C++ function named buddy resize, which has its declaration in the dip.h file. And yeah, so we get the pre-processed output as simple as that. This can then eventually be passed to the model function, and then we can get the output which we want. So let's now consider the case of single channel 2D image filtering. Now we do provide many image processing operations, but for the sake of this talk, I'm going to be considering the case of 2D image filtering. So the figure on the left depicts the usual way of doing this. So you can see that all of the individual elements of the kernel are accessed step by step and are then fused, multiplied, and added with the overlapping pixel elements in the input. And the final output is then stored in the output container. Now this basically gives me the output for just one pixel and uses 9 iterations. And the figure on the right is our approach to do this. So I want to highlight this, that the fact that we are using the vector dialect in MLIR essentially provides two major benefits to us. So the first benefit is that we do not have to worry too much about the lower level vectorized code generation, since we can target a generic abstraction, and the LLVM backend will take care of the code generation for AVX2, 512, Neon, and all those backends. And the second advantage which we get here is that the vector dialect is capable of accepting the vector as an input with more flexible sizes. So we don't have to worry about the lower level vector register size, and we can actually provide or actually create a vector with a size which is more suitable to us. This unlocks some improvement in the algorithmic implementation, so we can actually improve the implementation to better vectorize stuff. So you can see the figure on the right is a depiction of our algorithm. So starting from the top, we first load an element from the kernel and then broadcast it into a vector of size stride. So here the value of stride is considered as 3. So you can see that we simply broadcast it, and we also load a equivalent patch from the input image with the same stride. So the patch with which we load from the input image accounts for the fact of padding. So all of this image padding is automatically taken care by the algorithm itself. So once we get the image data and the kernel data, we just do a fuse multiplication addition, and we finally get the output which we require. So this output can then be stored back in the output container, and yeah, so we are good to go. So all of the results which we obtained from this dialect are compared with OpenCV, and they are in complete agreement. So so these two cases were considered by us for the boundary extrapolation. So you can see the first case for boundary extrapolation is constant boundary extrapolation. So we just take a constant and pad the boundary with it. And the second case is this replicate boundary extrapolation, wherein we are simply replicating boundary elements to get into the padding region. So in this slide, I just try to depict the effect of the anchor point position on padding. So you can see the extent and the direction of padding is actually determined by the position of anchor point. So this is just a simple case for 3x3 kernels, and we can see there are 9 potential different padding options available. So all of these padding options are automatically taken care by the algorithm, and the user won't actually have to worry too much about these things. So let me now present the performance data. So for the kernel sizes of 3x3, 7x7, and 5x5, we can see that the DIP dialect implementation performs reasonably well than OpenCV. The major reason for this is the algorithmic improvement itself. But for the kernel sizes of 9x9, you can see that we are losing performance on AVX2 and SSE, and are just marginally better on AVX5 and 2. So the reason for this is that OpenCV actually uses the fast Fourier transform to calculate the convolution output for larger kernel dimensions. So we have a fast Fourier transform in our dialect, but it's not yet well optimized. So it's a challenge to optimize fast Fourier transform, and we are still working on it to get performance improvements in that region as well. The performance data for the kernel sizes of 11x11 and 13x13 further reinforce this explanation. So these are the operations which we currently support in the DIP dialect. You can see that we support 1D and 2D image filtering along with image resizing, rotation, image morphology, as well as FFT and IFFT. So FFT and IFFT are not yet very well optimized, but the accuracy is completely checked, and we have compared our result by convoluting very large kernels on large images, and it's in complete agreement with OpenCV. So these are some of the examples of the DIP dialect operations itself. So you can see we can produce filter output. We can rotate the image with any angle we want, and we can also resize it with any size we want, as long as the size is not something out of bounds or a negative thing. We also provide, like I've also attached an example for the dilation and erosion thing. The reason I used different image for this example is because to highlight the output of the dilation and erosion itself. So you can see that the dilation image has less patches in the snowy region, while the erosion image has more patches in the snowy region. So finally, to conclude, we can say that we have these of the potentially unexplored regions in the dialect itself. So we can potentially target more hardware by lowering things down from the vector and memref dialect level to GPU dialect or other hardware-specific dialects. We can also integrate this with existing MLIR ML-based workflows, like maybe something like Torch MLIR. And we can also test the interoperability of the dialect with the lineal dialect. So lineal dialect tries to do things on the tensor level. So and as of now, the DIP dialect operates on memref level, but we can potentially raise this to see how it works with the lineal dialect. So to conclude, this is I want to convey. So we actually try to target the vector and all the low-level abstractions of the MLIR in order to reduce the code people use for vectorization, and all the while reusing the existing abstractions present in MLIR. So this should effectively lead to better performance with a less amount of code. So yeah, that I think marks the end of my presentation. This slide contains links to reach me, and the source code is also attached in the end. So you can have a look at this repository and try to see the benchmarks for yourself if you want to. So thanks a lot for your time, and yeah, I'm up for questions.
Okay, great. Questions?
Hi, thanks very much for this presentation. So the results you presented are for just selected operators, but I think the underlying idea is to be able to embed this in larger models and using, deep learning models. So have you tried benchmarking, like using this within a larger model and see what the impact on performance is?
Yeah, so I haven't actually integrated this with Torch MLR or anything. So that is why I added that as a potential scope. So I do wish to integrate this with existing MLR-based workflows, and I wish to integrate this with existing MLIR only based workflows, because the major utility which I have in my mind for this dialect is to support those frameworks which rely on MLR for getting their models working. I can potentially use this via the C++ library as well, but that would then like that is possible, but I'm not very interested on exploring that side of it.
So I'm asking because, like you mentioned, you created a dialect quite low level and you operate on memrefs, so you cannot use lineage. And basically you miss out on various optimizations happening at higher levels, like operator fusing. And for example, you had padding in there and there's tensor pad and you could be reusing that, right? So why start from low level rather than start at higher level to begin with? Because it seems like, you focus on vectorization, fantastic, but it's like you almost immediately want more.
Yeah, I get that. So the reason why we targeted memref is that it was easier for us to convert the image data into memrefs directly from the C++ land. So that easiness of converting things into that level was the first thing that got us started. However, I do get you, and that is why we are actually keen on raising this to the linalg level and try to see how things go from there. Although it might seem like raising things from memref to tensor and then eventually lowering that tensor stuff to memref back. But yeah, that should hopefully provide us some more optimizations on the higher level, as you mentioned. So yeah, I'm actually interested in testing that, and I hope I get more time to do that.
Can I have one more?
Yeah.
And how did you decide what operators to create? Like what inspired, so you presented a list. Why these? Why?
Yeah, so I most of the time I see for the pre-processing things, like people usually want to resize their images, or sometimes they want to rotate it for augmenting and increasing their data somehow by changing the existing set of data. So that inspired me. So I tried to target those operations which seem to me of greater utility. All of this is my personal decision, so I don't. I haven't actually, asked to the community like which operations they want. I did what I found interesting and what I thought will be useful. So yeah, I think.
I agree. Thank you. I agree with you that this is a missing piece in the overall infrastructure. So thanks very much for this.
Yeah, no worries.
Okay. More questions?
I think someone wants to ask a question in the back.
Yeah, let's start here.
Okay. Yeah.
You say that having a universal abstraction over these different vectorization instruction sets is problematic because the way you design it today might not be able to incorporate advances 10 years from now. Is the dialect kind of very different in that your dialect in 10 years can still incorporate all of the new developments, or do you foresee problems there?
As long as the compiler incorporates everything, I imagine we should get all of that for free. Since we are not dealing with vectors directly, we are dealing with the vector dialect. And as long as LLVM IR lowers down to the optimal code, I think we should get all of that for free. We are not dealing with vector registers by hand. So that is one of the reasons why we chose MLIR, because of this exact reason of being able to reuse these abstractions to get things for free. And everybody likes to get things for free for their work. So yeah.
Yeah, I'm just wondering, because LLVM doesn't always lower perfectly to these kind of a bit more niche instruction sets, and you might have more domain information to do that at the MLIR level as well. So I'm just wondering if you've tried that, right? Like having those machine-specific intrinsics at the MLIR level.
Okay, so do you mean that have I? If I understand this correctly, you're saying that have I tried putting hardware-specific instructions in the lowering pass itself, so that it generates things which are very much specific to the hardware? No, I haven't. I basically want to eliminate that. So that is one core piece of my problem. So I haven't tried that. And yes, your point is quite valid that there exists sometimes when LLVM IR doesn't lower to the most optimal set of things. But yeah, I think that is the end goal. Like we want things to work that way to lower to most optimal set of things.
Thank you.
Okay.
Let's thank the speaker one more time.